Welcome everyone to the BCS Hertfordshire YouTube live stream. If you haven't already, please take a moment to hit the subscribe button and then click on the notification bell to receive notifications of new BCS Hertfordshire streams and videos. Our speaker today is Paul Moggridge. Having gained a first-class honours degree in computer science from the University of Hertfordshire, Paul remained at the university to pursue his PhD. As part of the University Knowledge Transfer Partnership, he worked for Advanced Collection Systems in Hatfield. And just as we went into lockdown, he was appointed as a full-time academic member of staff. He is a BCS member, sits on the Hertfordshire Committee, and looks after our money as he's our treasurer. Now, before I hand over to Paul, let me explain that if you have questions for Paul, please let us know via YouTube chat or at BCS Herts on Twitter, and we will ask them in the Q&A at the end. So, without further ado, our speaker today, Paul Moggridge.
Thanks for the introduction, Peter, and thanks for this opportunity to talk as well. Today I'll be talking about data clustering. So this will be a brief introduction, going over the basics, so don't worry if you don't know anything, and you've never heard this term before. And also I'll be just talking a little bit about my research towards the end. So initially I'll start off with why data clustering exists, so what you can do with it. And we'll talk about how you can get started with data clustering as well. And we'll have a little bit of fun solving a made-up problem. And then in part two, I'll describe the different research opportunities in the field, and also talk a little bit about my research as well. And then at the end, hopefully I'll have some time to answer some questions. So part one. So data clustering is a technique within data science and artificial intelligence, a broader area. And artificial intelligence is a term that you've almost certainly heard. It's used on loads of different products, and you see it often on the news. And it's a term that's bandied around a lot. But it broadly means two things: understanding intelligence and building intelligent entities. And there's a lot of different definitions of artificial intelligence, but Russell and Norvig, at the start of their book, Machine Learning, a Modern Approach, put them into four really nice categories. So there's systems that think humanly. So this is like where we copy how the brain works. So for instance, we copy actually how the neurons actually work in the brain and try and come up with a system that learns and behaves just like a human and works like a human. And then there's systems that think rationally. This is where we copy what seems to be a logical process to solving a problem. Systems that try and act like a human, just put a facade on. And then there's systems that act rationally and just try to get the best outcome on a particular problem. So in fact, there's actually also behind the scenes, there's also sort of two different types of intelligence or artificial intelligence, and that's general artificial intelligence. This is where you're actually trying to create a whole intelligent entity. So you're trying to create an intelligent being that can actually solve any problem. Think like the Terminator or iRobot or any of those, or Wall-E or any of those particular movies where you've created an entity that can handle any situation in an intelligent way. And then there's also actually like functional intelligence, where you're just trying to solve a particular problem. So maybe like a chess playing algorithm, for instance. So there's those two broad categories, and of course within there's four different definitions. But what is data science? So that's artificial intelligence. Data science is quite cross-disciplinary, and there's three main ingredients you need, which is actually summed up by a very famous Venn diagram, which I've just linked down there as a point 2 in the PowerPoint. And there's three different ingredients. One is technology. So this is some programming skill in Python or R. You may know how to program in other languages, and Python's quite a friendly language to pick up. So if you already know a programming language, it's quite easy to get started. So you need some knowledge technical knowledge to hack things together, to get a system built, to install the software, and to interact with the libraries you'll need. The other ingredient you'll need will be an overview of maths and statistics and the algorithms and what they do. You don't particularly need a in-depth knowledge of everything, exactly how it all works, linear algebra and etc. You just need to understand an overview level of where the algorithms fit, what they're for, and what their limitations are. And then the third and final piece of data science is actually domain knowledge or expertise. So this is known about a particular field. For instance, you might be applying data science to a biological problem or an engineering problem or maybe a marketing problem. So those are the three things you need, and sometimes you'll see people that have just two of these or just one of these, and that's and then that's sometimes it'll be quite dangerous. So, for instance, if you have just technology and some domain expertise, but maybe lack knowledge of how the algorithms should be used, you can then get some false statistics and end up going down a potentially wrong path. So having an overview of all these three things is really what data science is. Because sometimes it can seem like a bit of a hyperbole term, a term that's a bit of a marketing ploy, but really what data science is those three things combined. Generally, data scientists follow the knowledge discovery and databases process. So this is a 5-step process which takes them from selecting data right up to actually extracting and presenting knowledge from the data and information that they've processed. So data clustering is unsupervised learning, and what this means is that the algorithm learns without labels. So if you think when we're a baby, we're shown mugs and chairs, for instance. We might see we'll see lots of different chairs and lots of different mugs, and whilst we don't know what they're actually called initially, we don't know that all the mugs are called mugs and the chairs are called chairs. We do recognize that these are two different objects with different properties, and that's essentially what unsupervised learning is recognizing the different types, different groups in data. And it's the opposite of supervised learning, which is where you do have the labels. So that's where you would show it a mug, you'd show the algorithm a mug, and you say this is a mug, and try and memorize all the different items that you would show it, all different particular samples, all different mugs, different types of mug you have. So there's two different ways data clustering can be used, and one is in an exploratory way. So that's where you're using data clustering for data clustering's sake. So you're essentially the meat in the sandwich is the data clustering. This is where you're trying to actually find the stereotypes in a data set. You're trying to group the different types of things. So, for instance, you're trying to find the different types of person in a database of contacts, or you're trying to group different parts of an image, for instance. The other way it can be used is as a pre-processing step. So this is where you intend to use supervised learning later on. So you would essentially run clustering as a pre-processing step to group data, and then apply labels to those clusters, and then use supervised learning. So to bring this to life with an example, imagine you've got a self-driving car, and you've been sending it driving around wherever you may live all day, and it's picked up and been videoing everything that's around it all day. So you've got all these thousands and thousands of images, and so what you could do is you could run data clustering on all of those images to find the different images, groups of images within all of that data. So you might find that you have a group of stop signs and a group of trees, for instance. And you could recognize, you could then just from the data clustering will give you the two different groups. Group 0, maybe the signs, and group 1, maybe the trees. And what you can then do is you can then go and label group 0 as the signs, group 1 as the trees, and apply that label to all of the instances in the groups, and then run your supervised learning step to then train all of the to train a supervised learning algorithm on all of that data. So you can say, so then you can show that supervised learning, okay, this is a tree, all the different examples of trees, and this is a sign, instead, rather than what we had before, which is unlabeled data. So that's the two different modes it can work in, and of course humans are fantastic at data clustering. We're excellent at recognizing different features, different objects in images, and grouping different types of people or scenes and situations. But where clustering comes really in handy is where we have data that's in more than 3 dimensions that we can't visualize, for instance, or there's just too many instances to go through, and that's when clustering really comes in handy, because we can then get a machine to do this in more than 3 dimensions or on a very large data set. So here's that knowledge discovery and databases 5-step process that I mentioned earlier. So data clustering is really a machine learning technique which tries to maximize intercluster similarity. So we're trying to get those groups as tight as possible, and maximize intra-cluster dissimilarity. So trying to get those groups as far apart as possible. So trying to find the objects that are most different and most similar in a data set. And of course, data clustering is somewhat subjective. So it depends what columns you provide to your cluster algorithm as to whether you get a meaningful result. Cluster algorithm will find the different groups in a data set, but whether those groups are meaningful is something you have to really validate with a human expert or against a set of labels. But of course, we don't tend to have a set of labels in data clustering unless you're doing it as on a data set which already has labels and you're just doing it to test an algorithm, for instance. So if maybe all that talking I've just done didn't quite land and make sense, here's a visual example. So in the background, we can see we've got some of my old toys. This is a Connect for anyone who remembers. And some of them are faded in the sun, and some of them are lighter than others, and some of them are more colourful. And also in the lighting of the picture as well, that they're all different colours. Although there's definitely 3 different pieces there. There's the yellow pieces, the green, red, and orange. And then in the foreground, we can see we've got 2 axes. So we've got a green axis and a red axis. And I'm going to have to apologise to any painters, any artists in the audience at this point, since in computer additive colour, when you have green and red together, you get yellow rather than the sludgy brown if you mix most red and green paints. So we can see we've got these white X's that seem to conform to 4 clusters, and up in the top right corner of the foreground, we can see that we've got those X's are representing yellow pieces. So we've got all different yellow pieces there, but we can recognize that they are all one thing by applying clustering, which is those circles you can see. It might be a little bit hard to make out. At the centers of those groups, so we can say what a typical orange piece is, what a typical yellow piece is, and so on. So it's about finding those different groups, even though all the objects in the dataset might not be exactly the same. So hopefully you're excited to get started with data clustering now, and or maybe you're even thinking of a data set, or you have a problem in mind maybe. And thankfully it's very easy and fun to get started with data clustering and data science in general. There's one very easy to install package called Anaconda, and if you search this up on Google, you'll easily find this. And I believe you can install it on all operating systems, Linux, Windows, Apple, and I think you can install it on Android, I believe, as well, or some sort of version on Android. But essentially, this is a packet installs loads of different useful tools and libraries all at the same time, and provides an environment to update them as well. So It makes it very easy to set up your environment and get started very quickly. And you'll need to be able to one thing you'll need to pick up is some ability to program in Python to use this. You'll open something called Jupyter Notebooks. For instance, is one of the several editors that it installs. And you can then type Python code, which accesses libraries like scikit-learn being one of the very important ones, NumPy and pandas also being very important for loading your data. And then you can actually apply data clustering. You can do pre-processing steps and data clustering on your home PC. So today we'll go through an example. I've created a very simple and trivial and somewhat silly example. And if you have a browser and you're able to, on your desktop PC or a laptop, you can go to this directory on this link URL on screen, and go and git clone the code, or I think you can download it as well, and get the notebook file that I'm going to be working on for the next few slides. So imagine you're a detective, and we've been called in to solve a silly made-up crime. So there's been a burglar who's been breaking and entering at the university, smashing through the windows, and stealing all the precious clustering research. And there's 3 suspects, A, B, and C. And each of these suspects have been found to have glass fragments in their shoes. So we're taking a few liberties here, but imagine the university doesn't want to smash any more of their windows. And the police department have a collection of over 200 glass fragments already, and some of these are labelled. So here on the right, we've got a silly visualization of maybe some of the glass pieces the police have, and they've got labels for some of them. So they know some of them are from windows, some of them from bottles and bulbs, but they don't directly match any of the pieces of glass that are found in the suspect's 3 shoes. So they've sent all these pieces off to the lab and analysed them for all the different elements they have, and it doesn't directly match any of the ones they have labelled. And so a bit of a dead end, if not for clustering here. So this is actually a real data set which you can download from the UCI dataset repository, which if you Google UCI glass dataset, or you go to this link down at the bottom of the PowerPoint, you'll find a fantastic repository of loads of datasets, not just this dataset, which you can use to practice all data science algorithms, so classification, clustering, pattern recognition, and these datasets often have labels, so you can examine the performance of your clustering. So this dataset that we've chosen today to solve for this imaginary crime is the glass dataset, and this has 9 features. I'm not going to profess to know about glass at all. I recognise these as elements, so this is, I suppose, the different makeup of the glass, and maybe some kind of indication of how sparkly it is, some kind of refractive index. So here's the top 10 rows of the dataset, and we can load it in using pandas. You can just see down the bottom of the PowerPoint, it's very simple. There's the one line of Python to essentially load the dataset, and the dataset is essentially in a CSV format. So the next step is to standardize or normalize the dataset. So this is helpful because it brings everything into the same scale. So we might have some attributes that are very high numbers, some that are very low numbers, and this can skew and put off clustering algorithms. So it's important and lots of different machine learning and artificial intelligence algorithms. So it's very important that we normalize or standardize the dataset first. So in this case, we've chosen normalization, and we've normalized all the values in the dataset between 0 and 1. So for all of the different elements here, we've got a score between 0 and 1 for how much the glass contains. So another pre-processing step now is to maybe reduce the dimensionality. So this also has a side effect of making it easier to visualize, which is why we're doing it here. Although it can also be very useful to avoid very high dimensional data, because cluster algorithms suffer from a thing called the curse of dimensionality, and like many algorithms, and the further and the more dimensions you have, essentially, the harder it is to recognize. The more sparse the data becomes, and the harder it becomes to actually recognize clusters in. So sometimes it's useful to reduce the dimensionality, and one tool to this is a principal component analysis. So this essentially, in simple terms, squashes axes together, and you lose some of the data each time you do this. So if you imagine you had two axes, and then you had effectively a sausage of data running along the XY diagonal, you squash those two axes together, you wouldn't lose that much information, since there's a fair amount of correlation between those two axes. So here on the right, we can somewhat see that. So if we just squash all of our 9-dimensional data down to just 1 dimension, we'd keep about 40-ish% of the explained variance of the information in the data set. If we went to 2, we'd give about 60%. To 3, we'd give about 70%, which is what we've gone with here. So we can see on the left here, we've got a 3-dimensional plot of the data reduced from 9 dimensions down to 3. And again, you can see the code there, and the code's quite simple and easy to follow, hopefully, if you're familiar with programming in Python, which is a very useful language to learn. It's one of the most upcoming languages at the minute, and Stack Overflow is completely full of support for programming with Python. And I think they actually recommend it as one of the best languages to learn right now for everything, not just data science. So moving on to another pre-processing step, now we're removing outliers. So there's maybe a few accidents that happened in the lab, and we've got a few strange values, or maybe there's a few strange pieces of glass from very particular applications of glass. So we've removed those using a density-based outlier detection algorithm. So this is the local outlier factor algorithm, and that's reduced the dataset down from over 200 instances down to 171 instances. This is useful because it stops because having outliers can skew your data for your machine learning algorithms like clustering, classification. And now finally onto the actual clustering. So you can see that a lot of a data scientist's job is actually pre-processing the data. It's a lot of work speaking to experts and pre-processing the data, gathering the data, pre-processing it is maybe 90% of the job, and then the 10% of the job is actually clustering data. So here we are using the simplest type of clusterer. A lot of people would agree the simplest type of clusterer is the k-means clusterer. So this is a simple algorithm which essentially, you can see those. You might be able to see those two green dots in this figure here on this slide, and those two green dots are initially randomly placed in this space, and we then ask, the first step of the algorithm says, okay, which points are nearest to each of these points, and then take the average. The second step is then take the average of each of those points for each of those for those two clusters, and then that of course updates the positions, and then that mean is used to update the position of those two clusters, and then again the algorithm repeats which dots are nearest to me, which instances, which rows of data are nearest to me. Okay, now take the averages of those two and update the positions of the centers until they converge and they stop moving. And that's what we can see here. We can see that those two green dots have stopped moving at these 2 points, best representing the two clusters we have. And k-means is a hard clustering algorithm, and what this means is that points are either cluster 1 or cluster 2. They're either the pink cluster or the blue cluster. They're never in between. There are soft clustering algorithms where each point is given a percentage. So ones towards the middle might be 60-40 or 70-30 each of the clusters. Whereas in k-means it's hard clustering, hard membership, and it's either cluster 0 or cluster 1. So Now we can plot our suspects, pieces of glass, in this space. So from the information we got from the lab, we also performed principal command analysis on the suspects data as well, and we can see those represented in this figure on the right here as A, B, and C, a red A, B, and C. And we can see that A and B seem to belong to the blue cluster, and that C seems to belong to the pink cluster. This is fantastic because now we can get an idea of who committed this crime. So using those few labels that the police had, those few pieces of glass that they knew where they come from, we can see that the pink cluster is probably made up of window glass, and that the blue cluster is made up of likely made up of other glasses, so jars, tumblers, bulbs, bottles, and other non-window glass. Of course, this is actually a real data set, and so these two clusters here might, you notice that the pink cluster is possibly made up actually of two clusters. It's because the data set contains lots of different types, different types of window actually. So this could be car windows and normal windows, but essentially we can see that the pink cluster is very likely to be a window glass, and hence we can solve our crime. And we can recommend to the police that it's possibly suspect C who has been breaking in and stealing all that precious clustering research, since they seem to have window glass in their shoe. So of course that was a very silly example, and not very and maybe not 100% realistic, but there are some common applications of clustering. So one is recognizing different types of landscape in satellite imagery. So satellites flying over the ground and can see different types of ground, and this can be identified. Forests, desert, things on fire possibly. And another use of clustering is to recognize different types of people, stereotypes of people using a service, and try and cater each of their needs. Another use is, as I mentioned, possibly self-driving cars as a pre-processing step to handle large amounts of data. And there's countless biological applications, which of course are beyond my understanding. But there's a stronger those experiments tend to produce a large amount of data and lend themselves to clustering. So part two, I'll now talk a little bit about my research and the different research opportunities in clustering. One of the fantastic things about clustering and well, in fact, artificial intelligence in general, is that the field's only been around since the 1950s. So there's still room for Edisons and etc. And in this field, and maybe unlike there is in other fields, there's still room for major discoveries to be made. And here are some of the open challenges in clustering in particular. So one of the challenges is creating stable and consistent algorithms that always cluster data in the same way reliably, and actually can handle data that's been pre-processed less. So as we collect more data and we want to do a live real-time machine learning on it, we need algorithms that are robust to things like outliers and initialization settings. They can choose their own parameters. So creating algorithms that are more robust and automated, handling bigger data. There's evidence that shows that the data sets that are being posted online are only tending to increase in the number of rows they contain. And dealing with high dimensional data, we've got systems with more sensors that we can end up with data with higher number of dimensions. We must be able to handle these challenges. Of course, one of the challenges particular to clustering is actually interpreting the results and creating metrics that are meaningful. And of course, creating algorithms that suit particular domains, or creating algorithms that are very, very general, could be applied to any problem. You don't need to assume a particular model on the data before you start. You don't need to look at your data too much before you apply the clustering algorithm. And another exciting area is semi-supervised clustering. This is where you tell it a couple of the points are not in the same cluster, and maybe a couple of the other points are in the same cluster. So you almost give it a helping start before we start actually applying the clustering algorithm. So my research is probably on the first one of those points, creating more robust algorithms that require less pre-processing steps, in particular less pre-processing of outliers. So we can see here on the far left, the standard approach to outliers is what we did earlier, is removing rows of data. So we can see that row 3 there is possibly an outlier, so we've removed it. Another approach, maybe not so much to outliers, but this is one of the things that inspired my research into instance-weighted clustering, is feature weighting. So this is where we weight the columns with different amounts of importance. So we can see that column X there is separates the data quite well. Column Y doesn't do so, doesn't separate the data so good, and so on. So in some ways, instance weighting clustering, which is my research, is a hybrid of these two ideas. So we're applying applying a weighting, but we're applying it per row rather than per column. And also linking back to the previous example, I use the local outlier in recent work. I've used the local outlier factor algorithm to recognize to actually create the weights for the clustering algorithm. So to decide which points to pay most attention to, which instances should we pay less attention to. We're not totally removing them from the dataset. We're just taking them less into consideration as we calculate the positions of those centroids, those green dots we saw earlier. One of the algorithms I created is one that calculates the local outlier factor, which points are most likely to be outlying over the whole data set at the start. And here's a example of that in action. So you can see that those black circles represents the chance that they're an outlier. And we can see the red points moving to go to the centers of those clusters and taking putting less weight on those instances that have the large black circles around. We also create another version of this algorithm, an iterative version, which recalculates those weights for every cycle of the algorithm for each cluster. So in this GIF, you'll see the cluster, those black circles changing sides each step of the algorithm as we get a bit better picture of where the centers are. So that's my research in a nutshell, and thank you very much for your attention. There's a couple resources you can go to if you wish to learn more. There's an O'Reilly book, the Python Data Science Handbook. That's a very practical and excellent introduction to the tools that we've used for the example today and in general. And of course, install an Anaconda. And if you're particularly interested in research and the cutting edge of data clustering, then there's a book, Data Clustering Algorithms Applications, which is quite fairly recent, gives a fairly recent summary of the field. So thanks for your time, and hopefully I'm happy to answer any of your questions. Thank you.
Okay, well, thank you very much indeed for that, Paul. Very, very informative. You talked about unsupervised learning, and you talked about trees and stop signs. You're probably too young to remember there was a sort of classic story about the military getting hold of neural networks, and they were interested in trees, and they were also interested in tanks. And of course, we camouflage tanks as trees. And so they thought, wouldn't this be a wonderful idea to get the neural networks to identify the tanks from the trees? And they did the unsupervised learning. And when they put it out into the field, they found it was an absolute disaster. It couldn't tell the difference. And it turned out that one of the issues was that with unsupervised learning, you don't really know what you're learning. And it turns out that the photographs of the tanks were taken on a dull day. And what the unsupervised learning has been doing is looking at the light levels in the photographs.
Yes. Yeah.
That's probably a classic problem.
Indeed, yeah, it really is. The quality of data you put in is critical. I think there's a saying, garbage in, garbage out, and And yeah, as I mentioned earlier, the pre-processing of the data is really critical, and creating a good training set. That's more in supervised learning. We create like a training set, and in that case, it sounds like there was a lot of these dull images, and of the tanks or the trees, and they end up associating that as the thing that it associated with a tank or a tree, rather than the true properties. So pre-processing your data set and selecting good data is really key to a successful knowledge extraction from the data. It's really the majority of the job, really.
Okay. Could I ask you a question about your PhD? What sort of stage are you at the moment, and where is your research taking you?
Right now I'm about halfway through, and I'm very fortunate to have some fantastic supervisors who are very patient and supportive. And currently, right now, I think my area of focus is creating algorithms that require less pre-processing. As you can see, it's a lot of the job, and creating algorithms that are more robust and can not be affected by outliers, etc. And doing that using instance weighting is really the focus of my research. I'm probably about halfway through now, I believe. My supervisors may disagree with that.
Okay, well, normally at this point, we'd say thank you very much and ask for a round of applause, present you with a bottle of wine and a book. But we're having to do things virtually at the moment. So may I thank you very much indeed, Paul, for your contribution this evening. It's been fascinating to talk to you. And could I also thank everyone who's been watching and for the questions that we've received from the audience. If you've enjoyed this, please make sure that you push the like button on YouTube and that you let us know your thoughts in the comments below. If you haven't already, please subscribe to our channel and hit the notification bell icon to be informed about new BCS Hertfordshire content, and look out for more videos coming soon. I wish you well. Good night for now.
Yeah, very welcome. Thank you.